So as you clicked on this video, I assume that you know a bit about SpaceX and the Falcon 9 rocket, and that it can land itself on the launch pad or on a drone ship out to sea. But how hard can it be to replicate this on a very small budget? I guess I'm going to find out. So there are three main things that you need to get a rocket off the ground and into space. The first one being thrust. Obviously without thrust you're just going to sit on the launch pad, not going to go anywhere. The second one is stability. Now without stability the thrust is pretty much useless. We've all seen those videos of model rockets taking off and just spinning out of control. So you need the stability to keep the thrust pointing downwards and the rocket nose going upwards. And the third one is control. Now for model rockets you don't really need control, you just have the thrust and the stability and the rocket should continue going straight up until the fuel runs out. Space rockets, for NASA or SpaceX, you need some kind of control to get them into a correct orbit around the Earth. So it's quite easy for some to get the stability and the control confused sometimes, but they're actually completely different things, which I will explain later in this video. Now there are two main types of rocket engines. There are solid fuel rocket engines, which you'll probably know if you've ever launched a homemade rocket. Those small little brown tubes are basically solid rockets, solid fuel rockets. They have fuel mixed with an oxidizer inside, and once you ignite them, they burn like a firework and disappear into the sky. Now the disadvantage with solid fuel rockets is you have no control over them. Once they're ignited, they're gone until the fuel runs out. So this is why the second type of rocket, liquid fuel rockets, are used for the Falcon 9 and most of the other, larger space rockets. A liquid fuel rocket has two tanks, one filled with fuel and one filled with oxygen, and they mix together in the engine at the bottom, which ignites them, and they're expelled out through the nozzle at the bottom of the rocket, propelling it upwards. Now, the advantage of the liquid fuel rocket is you have full control over the throttle output. You can turn it off, turn it on, vary it, etc. But the disadvantage is I can't get my hands on one within my budget for this project. So don't get mad at me, but I'm not going to use a rocket engine. What I'm actually going to do is I'm going to duct some propellers, so essentially make a ducted fan, use two motors with two propellers inside of the rocket, which will suck air in through either the top or the sides and expel air out the bottom. It will essentially do exactly what a rocket does, where it just pushes air out the bottom, or any kind of gas out the bottom, but it will be a lot cheaper for me, and also I'll have full controllability over it, unlike a solid fuel rocket. I know it won't produce smoke and flames and sound really cool, but for this project it will do exactly the same thing as a rocket would do. So yeah, deal with it. The stability of a rocket can be very complicated, so I'm just going to run through the basic requirements for the natural stability of a rocket. So the most important requirement for a rocket to be stable within the atmosphere is to have the centre of mass in front of the centre of area. Now, to work out the centre of mass on a basic level, if you put the rocket horizontally and you put a pivot somewhere on the rocket, the point at which it balances is the centre of mass. So if you add weight to the tail of the rocket or to the nose of the rocket, that will shift the centre of mass around. Now to calculate the centre of area is slightly more complicated, but a basic way to do it if you want to build a rocket at home is to cut a cardboard cutout of your rocket, and because the cardboard cutout is uniformly dense, the point at which that balances will then be the centre of area. So essentially from the centre of area, all the area at the top of the rocket will be equal to the area at the bottom of the rocket. So adding larger fins will shift the centre of area down towards the nozzle of the rocket, and reducing the size of the fins will shift the centre of area upwards. So depending on the size of the payload, you may need larger or smaller fins, or the opposite way around. Now as the Falcon 9 re-enters the atmosphere backwards, the centre of mass needs to reverse positions with the centre of area. Essentially it will be like throwing a dart backwards. The mass can't be behind the fins at the front. Now from observations I assume that the centre of mass is shifted downwards as soon as the second stage is deployed. the second stage is quite a large mass on top of the rocket, and as soon as it's separated, the rocket will then balance at a lot lower position on the first stage. Now, I'm not sure how much this shifts the mass and all that kind of stuff. I'm just sort of going by assumptions from what I've observed. So to move the centre of area upwards, the Falcon 9 deploys small grid fins, which essentially act as the fins on a dart, increasing the area at the top of the rocket, and as it moves the centre of mass downwards, it will then fall straight down like a dart would. So although it looks like it's flying backwards, aerodynamically and rocket stability wise, it's a rocket facing forwards. You might be wondering what I meant when I said stability is different from control. Now, control can be used to stabilise a rocket, but a rocket should be naturally stable in the first place, and the control just assists the stability. So how is the Falcon 9 controlled from takeoff up into space? Well, the easy and quick answer to say is that the rocket nozzle at the bottom of the Falcon 9 can pivot on a gimbal, and this will rotate the rocket. But how does it rotate the rocket? Now, all objects will have a centre of mass, as I explained earlier, is a point at which it balances. But it's also the point at which it will rotate. So wherever the centre of mass is on a rocket, the rocket will rotate about that point when it's in the air. Now, for those of you who have studied physics at school or whatever, you'll know what a moment is, or it can be called a torque. It's essentially when a force is applied at a perpendicular distance from the pivot point. The pivot point on a rocket being the centre of mass. So if you apply a force at a perpendicular distance from that centre of mass, it will cause the rocket to rotate. Now, when the nozzle of the rocket rotates, the thrust line is thrown off to the side of the centre of mass. And that perpendicular distance between that thrust line and the centre of mass causes the rocket to rotate. Now, once the Falcon 9 has turned its engines off in space, deployed the second stage, and is ready to re-enter the atmosphere for landing, it needs to turn around. Now, because it's turned off its main engine, it can't just pivot the nozzle to rotate the whole rocket. Instead, it has small little rocket jets on the top of the rocket, which thrust gas horizontally out the sides, and as I mentioned earlier, that produces force at a perpendicular distance to the centre of mass, and therefore rotating the rocket. So these small jets of gas aren't that powerful and can only be really used in the vacuum of space. As it starts to re-enter the atmosphere, if the rocket spins out of control, these thrusters will not assist with the control of the rocket, which is where the grid fins come in again. The grid fins are on pivots, and they can rotate, and basically, like on an aircraft, they work as the flaps, and they direct air in different directions to control the rocket down towards the landing pad. So as the rocket approaches the launch pad, the velocity of the rocket obviously slows down a lot, which means the air flowing through these grid fins isn't as fast and basically makes them less useful. So there has to be another control method, which is where the gimballing of the main engine and also the jet thrusters at the top of the rocket come back into play. So pretty much what I've explained here is there's three phases of flight. There's the control in the vacuum of space, which uses the thrusters only. Then the re-entry, which uses the grid fins, the aerodynamic variation of the grid fins. And then as the rocket slows down and the grid fins become useless, the thrusters and also the main engines turn back on to control the rocket. So now you might be wondering, how on earth am I going to replicate this control and stability method into a model rocket? I think it's probably easy to explain if I just get on with the video. Let's get building. So I'm going to pause the video here for a second and explain a few things. Basically, the weather forecast said I had 2 clear days of low wind before high winds struck for about a week or so. So I rushed out to test fly the rocket and didn't really get much footage of the rocket before I flew it. So before I show you the flight attempts, I'm just going to explain the control method that I chose to go with. So as I mentioned previously for thrust, I've got 2 propellers and 2 motors mounted inside the bottom of the rocket. They both counter-rotate each other, so they spin opposite ways. This is to counteract the torque of each motor and make sure that the rocket doesn't just spin around. For attitude control, the roll and pitch axis, on the very top of the rocket there are 4 very small motors and very small propellers mounted horizontally. These basically act as the small thrusters, the gas thrusters on the real Falcon 9, and apply a force at a perpendicular distance from the centre of mass. The battery that powers the whole rocket is mounted just at the top of the grey spray painted section, and as the motors are at the bottom, the centre of mass is relatively low on this rocket, so it should have a high moment about the centre of mass. So anyway, let's get on with the first tests. So as the rocket needed to be stabilised via some kind of gyro or accelerometer, I chose to go with a flight controller from a drone, essentially made for a racing drone, and I had to reprogram the code a bit to control this, which is why you'll see me walking back and forth quite a lot and occasionally grabbing my laptop to adjust the code, because it needs quite a lot of tweaking. So this is a good example of what I meant by it needs a lot of tweaking. Basically, I need to program which direction the gyros need to go and also how sensitive they are. And on this occasion, they were just too sensitive, which caused them to overcorrect and eventually causing the rocket to fall over. So again, the rocket overcorrected, the gyros were still too sensitive, and unfortunately this resulted in the top stability module, the small motor thrusters at the top, breaking. So instead of repairing that, I decided to build a completely new rocket. And you know how I said I only had 2 days of good weather before the wind started picking up? Well, I stayed up very late that night building a new rocket, and because I had to get it built very quickly, I didn't record any of the build, so let me just show you the final rocket now. So this version 2 rocket is very different from the first rocket. The first rocket had the weight very low down and produced a perpendicular force at the top of the rocket, whereas this rocket has all of the weight up high. You can see the battery sticking out the top there, and at the very bottom it has a thrust vectoring system to produce a perpendicular force right at the bottom. So it's essentially completely the opposite to the version 1 rocket. The other difference is that it's about 75% the weight of the version 1 rocket. It only has 1 motor instead of the previous 6 motors on the version 1. And the way that I've got around doing the torque from the motor, making the rocket spin, is the thrust vectoring system at the bottom can vector the thrust in a spiral sort of way to counteract the torque. Initially, to prevent it falling over, I decided to hang the rocket from a tree using some surgical cord elastic, I think it's called. It's basically just a big rubber band, which allows the rocket to bounce up and down. So I can apply some thrust to it and just see how it kind of corrects. Using this method allowed me to tune the rocket a bit. I was able to tune the gyro sensitivity to correct a certain amount. It didn't give the rocket full, freedom to control itself because the elastic would always pull it to the side if it started drifting or something like that. So I could never really get it to properly hover whilst hanging from the elastic. So then it was time to test the rocket for real. I decided to hold the rocket in my hand just so I can get a feel for when the thrust is about to hold the full weight of the rocket. Also, if the rocket's on the ground, it will tend to tip over if one of the legs dig into the ground. So just holding it about a foot off the ground really assists the rocket in trying to get into a stable hover. Is that loud? Is that a bit loud? One interesting thing is that it's programmed to hold itself level, with the legs facing downwards and the nose facing straight upwards. But because there was a slight wind on this day, you can see the rocket keep drifting to the left of the screen. And there was no real way to counteract this, because the rocket would just keep itself vertical and the wind would just push it along. It wouldn't automatically lean into the wind to hold its position. So you'll see me just keep pushing it off towards the right of the screen and then it drifting back. It was at this point that I realised this probably wasn't going to fly for very much longer. I could smell the motor burning out because this thing needed it needed pretty much 100% throttle just to hover. So the motor was getting extremely hot because it's not designed to hold that kind of power for that long. But for the video I just thought might as well keep flying until it burns out completely. In 3, 2, 1. Yeah, it smells really burnt out right now. So I think it's time to call it a day. So was this a success or was this a failure? I'll leave that to you to decide. From my point of view, I managed to get a polystyrene tube to hover using a physics technique of thrust vectoring that wasn't too dissimilar from the real SpaceX Falcon 9. I definitely think this project could be revisited if I can find some kind of way to increase the thrust without burning out the electric motor. But for now I'm going to have to put it to rest because I need to find a new power source. The wind is picking up and quite honestly I am tired of building polystyrene tubes. I'd like to thank you very much for taking your time to watch my video. Don't forget I have a Patreon page if you wish to support me. If you're new to my channel, please subscribe, and if you like the video please leave a thumbs up. Thanks once again for watching and see you next time.